Okay, welcome back, everybody. We're happy to have Gidon Orelowitz, who will tell us about Newell-Littlewood numbers.
So yeah, thanks for introducing me, and yeah, thanks to the organizers for having me speak here today. So yeah, today I am going to be talking about the Newell-Littlewood numbers. So the structure of this talk is, first I'm going to talk about the Littlewood-Richardson coefficients, which are a set of coefficients maybe you've heard of before. They're in algebraic combinatorics, at least the part that I work in, they're a pretty big deal. And I'm going to talk about where they come from, why we might study them, and a couple of problems involving matrix eigenvalues that they solve, and what we know about their positivity. And then once we have all of that groundwork, we'll talk about the Newell-Littlewood numbers, which are numbers that me and my co-authors have been working on for a while. And hopefully I'll convince everybody here that they are similarly worth studying because they show up in similar places of tensor product multiplicities. They solve matrix eigenvalue problems, and I'll speak about what we know about their positivity. So if we're going to talk about Littlewood-Richardson coefficients, we have to first understand what a partition is. Simply put, a partition is just any weakly decreasing finite sequence of non-negative integers. So for example, 3, 3, 1 is a partition, and we can represent it by its diagram, which we can think of as 3 boxes, then 3 boxes, then 1 box. And we say the length of a partition is just how many rows it has. So this partition has length 3, and the size of the partition is just how many boxes it has. So in this case, this partition has 7 boxes. So one of the reasons we might care about partitions is because the partitions with the most n parts enumerate the irreducible representations for GLN, the set of n by n invertible matrices. So if you take the tensor product of any two representations, you're going to get another representation, and because GLN is a reductive group, you can decompose it right back into the irreducible representations. So we can look at this tensor product decomposition, and we're going to get these. Each representation is going to have a specific multiplicity, and we're going to define these multiplicities as the Littlewood-Richardson coefficients. So there's a number of basic facts that we can say about these Littlewood-Richardson coefficients. So firstly, the act of taking a tensor product is commutative. So it should be symmetric in lambda and mu. And another thing is, so we can define a Littlewood-Richardson triple to just be a triple of partitions with positive LR coefficient. And one thing that we know about LR triples is that the sum of the size of lambda and mu has to equal the size of nu. And in particular, most relevantly for this talk is that the Littlewood-Richardson coefficients have what is known as the semigroup property. So a semigroup is just a group, except that you don't necessarily have an inverse element. So you still have to have a 0 element, you still have to be closed on the operation, you still have to be associative. And so it turns out that if you add 2 Littlewood-Richardson triples together, you get another LR triple. And so we can define the LR semigroup as just the set of all Littlewood-Richardson triples. And similarly, we can define the saturated Littlewood-Richardson semigroup. And the way we're going to define that is by taking rational partitions, triples of rational partitions, and the saturated group is going to be any triple of rational partitions where we can scale it up or down by a rational number to get a Littlewood-Richardson triple. So clearly the LR semigroup is contained in the saturated LR semigroup, because any Littlewood-Richardson triple, you just scale it up by 1. And obviously the other direction is not true because, for instance, the saturated Littlewood-Richardson semigroup contains fractional partitions, so like 1/2, 1/2, 1, which isn't going to be in the Littlewood-Richardson semigroup. But it turns out that this fractional business is the only difference between the two. And so in 1999, Knudsen and Tao showed that the Littlewood-Richardson coefficients are saturated, which just means that if you only look at the integer points of the saturated semigroup, you get back the usual semigroup. This is not obvious at all looking at the definition or even any of the facts that we know about them so far. But essentially what this means is that if you have a Littlewood-Richardson triple such that all the parts of all the partitions are divisible by the same number, you can just divide that out and you'll get another Littlewood-Richardson triple. And we'll talk about later on with the Newell-Littlewood numbers how this isn't obvious, or you shouldn't even take this for granted, even for nice coefficients. I'd also be remiss if I didn't just at least offhandedly mention that Littlewood-Richardson coefficients are the structure constants for a basis of these symmetric functions, specifically the Schur functions, which is most of what I do involves Schur functions. It's not particularly relevant for this talk, but I figured I'd just give a quick shout out to those. So one classical problem in math was to solve the matrix eigenvalue problem. So as a quick recap, a Hermitian matrix is just one whose conjugate transpose is itself. And thanks to the spectral theorem, we know that the eigenvalues of a Hermitian matrix are real. So we can just order them from greatest to least. And if they're all the same, if they're all non-negative, then that's a partition. You can correspond eigenvalues of Hermitian matrices, if they're all non-negative, to partitions. And so the classical matrix eigenvalue problem is, if you know that the sum of two Hermitian matrices is a third one, what governs the eigenvalues? Or if you know, like, are there a set of properties we can put on the triple of eigenvalues such that if they satisfy this, one could construct Hermitian matrices, so A + B = C. And Klyachko answered this problem in 1998 and said that this is exactly the saturated Littlewood-Richardson. Okay. So in particular, thanks to Knudsen and Tao, we know that if you're looking at specifically positive integer eigenvalues, then those are exactly going to be what the Littlewood-Richardson coefficients are, non-zero. So for instance, here, if you look at 2, 1, 2, 0, and 3, 2, that's a Littlewood-Richardson triple. And therefore it's in the saturated semigroup. And 2 and 1 are the eigenvalues of A, 2 and 0 are the eigenvalues of B, and 3 and 2 are the eigenvalues of C. It's easy to check that these are Hermitian. A plus B equals C. So now I'm just going to do a quick detour and mention that these Littlewood-Richardson coefficients are actually very well understood. We know exactly how to count them. And there are truly so many different ways to count them involving strange objects, or at least I think they're strange, including honeycombs and crystal lattices and whatever. So I just want to share, in my opinion, the simplest one to give you an idea of what these actually count. So we've talked about the diagrams for partitions. We can also talk about the diagrams of skew partitions, which are just what happens when you take a partition and remove all the boxes from a smaller partition. So 4, 3, 2, 1, take away 3, 2 gives you this skew shape. And we can also describe a sequence of positive integers as Ballot if at any point at least as many k's as k + 1s have shown up. So for example, 1, 2, 1, 3, 2 is Ballot, but 1, 2, 3, 2, 3 is not Ballot, because at this point, by the second 2, more 2s than 1s have shown up, so it's not going to be Ballot. So if we let a Ballot's tableau just be a filling of a skew shape such that it's weakly increasing on rows, strictly increasing on columns, and reading the word from right to left, top to bottom, in Hebrew reading order, so to speak, is a ballot word, we call that ballot tableau. And this counts the number of Littlewood-Richardson coefficients. So for example, if we look at the shape 4, 3, 2, 1, skewed out by 3, 2, and we fill it with 3 1s, 1, 2, and 1, 3, then we see that there's exactly 2 ballot tableau with those properties, which are these, because 1, 1, 2, 1, 3 is ballot, and similarly 1, 2, 1, 1, 3 is ballot. So therefore the corresponding Littlewood-Richardson coefficient is going to be 2. So this technically solves the Littlewood-Richardson problem, since we know what they count. Given enough time, we can always compute them. So this solves the matrix eigenvalue problem in particular. However, if these last 2 slides didn't convince you, you can take my word for it. These things are not easy to count once your partitions get large. Even if you fix the number of rows, like you say that Landon, you have at most 4 rows, as the sizes get very large, you could hypothetically, you could have a lot of different tableaux that you'd have to look at to check to see if they're ballot. It gets very messy. It could get, the time it takes to compute these could get exponentially large. So, but we're able to cut down on the time to compute if something's a Littlewood-Richardson triple or not. If we don't care about how many there are, we just care about finding is it 0 or non-zero. And to that, we have the celebrated Horn inequalities. So a quick definition to get started is that we have to just define this tau function. It's a very easy function. All you do is you're given a set and you just subtract I from the ith smallest element. So for example, 2, 5, you subtract 1 from the 2, 2 from the 5, and you get 1 into 3. That's going to be weakly decreasing. So that's a partition, specifically 3, 1. And what's nifty about this tau function, you can prove that it's actually bijects between partitions, between sets of n of k elements, and partitions with at most k rows and n minus k columns. So over here, there are 5 choose 2, 10 subsets of 5 of size 2. And tau, for each of them, tau spits out a different partition with at most 2 rows and 3 columns. And in particular, they're all unique, and this is actually all of those partitions. So this is a bijection. And so, and this tau comes in handy to describe the so-called Horn inequalities. So these were first conjectured by Horn in 1962 to describe the saturated LR cone, and then were proved 35 years later by Klyachko to actually do so. So the Horn inequalities are just certain parts of nu is less than or equal to certain parts of lambda plus certain parts of mu. And what decides which subsets of the indices are we taking? Well, we need the 3 sets to be the same size. And we need, if you take the tau of each of these 3 sets, we need that to be a Littlewood-Richardson triple in its own right. So you get this interesting recursive structure to it, where if you're given a triple of partitions and you need to figure out if this is a Littlewood-Richardson triple or not, you first have to see whether it satisfies all the Horn inequalities. But how do you generate the Horn inequalities? By knowing smaller Littlewood-Richardson triples. So for example, when n is equal to 2, we have 3 Littlewood-Richardson triples that are sufficiently small: 0, 0, 0, 1, 0, 1, and 1, 1, 0. And those correspond to the 3 Horn inequalities for n equals 2. Just a quick note. So you need the Horn inequalities, and you also need the condition that the size of nu is equal to the size of lambda plus the size of mu. And this is a size condition. So these Horn inequalities were originally devised to solve the matrix eigenvalue problem, is why Horn conjectured these. And here you can think of this size of nu, that's the sum of all the eigenvalues of the matrix, which is just the trace of the matrix. So all this is saying that if you want the sum of 2 matrices to be a third matrix, you need the sum of the 2 traces to be the sum of the third trace. Also worth mentioning is that these inequalities are not irredundant. So they are necessary and they are sufficient, but there are inequalities that can be expressed in terms of others. However, the switch to make these point inequalities irredundant is actually quite simple. You just replace the condition that the Littlewood-Richardson coefficient of the tau needs to be positive with you need it to be 1. And that's all you need in order to make them irredundant. We're going to talk about irredundancies later on and how it's weird that this is so nice, so to speak. But okay, so this is all talking about the Littlewood-Richardson coefficients. So now I'd like to move on to the Newell-Littlewood numbers. So this was a pretty neat trick. We pulled all of this interesting combinatorics and all of these cool facts and these matrix eigenvalue problems out of just studying the tensor product multiplicities for the general linear group. But so one might think, let's try other groups that are quote unquote simple, not simple in the group theoretic sense, but nice. And so we might sort of expand our scope slightly to, instead of just talking about GLN, we might talk about all the classical groups. So the classical groups are the general linear group, which we talked about before, the special orthogonal group, which is the set of n by n matrices that have determinant 1 and preserve a given symmetric bilinear form, and the symplectic group, which is 2n by 2n matrices that preserve fixed skew symmetric bilinear form. So these are the classical groups. And in Weyl's book, 1939 book, The Classical Groups, he came up with the so-called Weyl construction, which is an algorithm that for any partition of size n will give you a representation for either GLN, SO2n plus 1, SP2n, or SO2n. Types A, B, C, and D, if you want to think of it like that. And for a fixed classical group, this is a injection. These produce different representations, and these representations are going to be irreducible most of the time. So technically, if lambda has n non-zero parts, then the representations for SO2n are going to be decomposable into 2 smaller irreducible representations. For this talk, we're going to kind of brush over that, and hopefully you can just take my word for it that the math all works out if you treat them as if they were irreducible. So ignoring that small blip, they're all irreducible and they're all unique. So awesome. What would you like to do with this? I mean, we'd like to try and pull off the same trick. Once again, the classical groups are reductive. So if you tensor product 2 of these quote unquote irreducible representations together, you can break that down into irreducibles. And firstly, it's interesting, like this breaks down into these representations that Weyl constructed again, and they show up with different multiplicities. Obviously, these representations are going to be different for each of the 4 groups that we talked about. So these multiplicities are going to be different than just the Littlewood-Richardson coefficients. But there's certain things we can say about them. So for instance, we found that before, talking about just the coefficients themselves was the multiplicities themselves was interesting, but there's actually a lot of interesting math that could be done with the saturated coefficients. So we can likewise talk about the saturated tensor cone as just being any triple of rational partitions that you could scale up or down so that the multiplicity is non-zero. So just to give a very simple example, this is, if you look at the representations corresponding to 2, 2, and 2, these are different representations for different groups. So you'd expect different multiplicities of the various in the decomposition. So for instance, for the 3 new classical groups, we get different outputs. Go figure. But once n hits 3 and then goes more than that, couple of interesting things happen. Firstly, they for any of the classical groups, it stays constant. So this isn't expected. As the group changes, their decomposition could change. Certainly, for example, like a lot of weird things happen in the jump from 2 to 3. So like you can lose representations. So you can lose elements of your decomposition. So for example, here we have V32 in SO2n plus 1, and that just disappears as n goes to 3. You can add representation. You can, in this, for example, V321, V222, and V211 show up once n gets larger. And you can even have the case where the representation stays, but its multiplicity changes. So for example, V22 has multiplicity 2 in SO2n, but then it has multiplicity 1 when you go to 3. So the fact that nothing weird happens once we hit 3 and we keep going is by itself pretty strange. But what's even stranger is that not only do they stay stable, but they all stay stable on the same thing. That's weird. So there's something special about the number 3 in this. And in particular, 3 is 2 plus 1. This is a high level talk. So 3 is equal to 2 plus 1. And where did 2 and 1 come from? 2 is the length of the partition 2, 2, and 1 is the length of the partition 2. So this isn't a coincidence. It turns out that in general, we can call if whenever n is at least the sizes of lambda and mu combined, we get this stability, and so we're going to call this the stable range. But what about the other miraculous result? Well, that's thanks to Koike and Terada in 1987, which says that in the stable range, other than GLN, all of the other multiplicities are going to agree. So we've done this trick 3 different times for 3 different groups, and we get the same multiplicities. That should be a hint that these things are pretty special. And we're going to call these the Newell-Littlewood numbers. So independent of this representation theoretic definition, Newell and Littlewood were able to show that these coefficients can actually be described in terms of these Littlewood-Richardson coefficients. So in particular, you can say they're equal to this like sum over all triples of partitions of this 3-way product of Littlewood-Richardson coefficients. And just from this formula and what we know about the Littlewood-Richardson coefficients, there's a lot of stuff we can say about the Newell-Littlewood numbers. So in particular, by the same tensor products being commutative, we would expect the numbers to be symmetric in lambda and mu. But from this formula, we can actually see that exchanging the lambda, mu, and nu, all that means is you're just exchanging the alpha, beta, and gamma. So it's symmetric in all 3, which isn't obvious from the representation theoretic thing. Also, if we say that lambda plus mu is equal to nu, if you add that restriction, you actually recover back the original Littlewood-Richardson coefficients. So these are not just sort of an extension. These are not just an analog of them for other types. These are actually an extension of them. So we would expect any facts that are true about the Newell-Littlewood numbers to somehow be restricted down to being the Littlewood-Richardson coefficients facts. We also have we can define a Newell-Littlewood triple the same way that we defined a Littlewood-Richardson triple. And it turns out that for any Newell-Littlewood triple, by looking at this equation, we can see that the sum, and doing a little bit of algebra, we can see that the sum of the sizes of lambda, mu, and nu is even, which seems inconsequential, but we're going to come back to that in just a second. And lastly, because these Newell-Littlewood numbers are based on the Littlewood-Richardson coefficients, and those have the semigroup property, the Newell-Littlewood numbers inherit that semigroup property. And so we can again define the Newell-Littlewood semigroup in the obvious way. It's the set of the triples, and we can define the saturated Newell-Littlewood semigroup. Similarly, rational partition that scale up or down to make Newell-Littlewood numbers. And here, again, I'm just going to do a quick plug for the more algebraic combinatorics type stuff. These Newell-Littlewood numbers are also the structure constants for a basis for the symmetric functions, the so-called Klyachko functions, which we're not going to get into, but as you would expect from this, from the fact that the Littlewood-Richardson coefficients are a restriction of the Newell-Littlewood numbers, if you only look at the highest degree terms of the Klyachko functions, those are going to be the Schur functions. So that's how we preserve this structure constant statement. So I want to go back to this fact over here that for any Newell-Littlewood triple, the sum of the sizes needs to be even. Well, we can look at the triple 1, 1, 1, and by just a simple parity argument, again, high level graduate school math, 1 + 1 + 1 is 3, which is an odd number. So that's not going to fly. But if you scale everything up by 2, turns out that 2, 2, 2 is a Newell-Littlewood triple. So we have that 1, 1, 1 isn't in the usual semigroup, but it is in the saturated semigroup since you can scale it up. And therefore, these Newell-Littlewood numbers are not saturated. So we have integer points in the saturated semigroup that aren't in the usual semigroup, which is not great. That's the main nice fact that you would want to be true about these that isn't true about these. However, myself and my co-authors, Shelaine Gower and Alexandra Yong, have conjectured that this parity argument is the reason why saturation fails, but in fact, it's the only reason that they fail. So if instead of just looking at the integer points in your saturated semigroup, you looked at the integer points whose total size is even, then you would recover the original saturation statement. And we've been able to, using like a computer, we've actually been able to conclusively prove this statement for n less than or equal to 5. And then we've proved it for like up to large examples. So for maybe partitions like lambda, mu, and nu that are below, I want to say 10 or 12 for like n equals 6. So we have some data that suggests that this is a reasonable conjecture, but we do not have this. And this would be the analog and in fact extension of the Knudsen and Tau theorem from 1999 for saturation. However, we have been able to prove, myself and my co-authors have been able to prove this interesting statement about the saturated Newell-Littlewood cone, in that it agrees with the saturated symplectic cone for M. And this statement might seem obvious. I mean, we defined these Newell-Littlewood numbers in terms of the stable range for the SB2M. And in fact, all of the other classical groups, that's the whole reason we're doing this. But the key phrase here is that M is greater than or equal to N, not 2N. If we were just relying on the stable range, then for given lambda and mu, we would expect nu to conclusively show up in the saturated cone for whenever M is greater than or equal to the sizes of lambda and mu in the stable range. But here, M can be below the stable range. So this result, actually, you don't need the stable range for, which is pretty interesting if I say so myself. And I was talking about matrix eigenvalues before. That wasn't just me talking about things I find interesting, because it turns out there's a parallel problem for the Newell-Littlewood numbers. So there's countless ways that we can define the symplectic Lie algebra on 2n variables, and just pick your favorite skew symmetric bilinear form. But my favorite skew symmetric bilinear form is the one that defines the symplectic Lie algebra as just all matrices that are symmetric about the anti-diagonal. So that's one of the many definitions for the symplectic algebra on 2n variables. And the property, and this has the nice property that if you have an eigenvalue of such a matrix, then the negative of that eigenvalue has to have the same multiplicity. So these eigenvalues won't immediately correspond to partitions, but if you only take the positive half of the eigenvalues, that corresponds back to partitions. And you can go the reverse way by just taking a partition and then negating it. You now get a set of eigenvalues for some symplectic algebra matrix. So our version of the matrix eigenvalue problem is that if you look at Hermitian matrices with 2n variables that are also in the symplectic algebra, then we get back the usual matrix eigenvalue problem. When is the sum of two of those matrices equal to a third? Well, those triples of eigenvalues correspond to partitions by taking the positive half, and those partitions are exactly the saturated Newell-Littlewood semigroup. So that's a slightly more complicated statement because the partitions don't exactly align, but I think this example maybe will make it more obvious. 3, 4, 5 is a Newell-Littlewood triple. So in particular, it's in the saturated semigroup. And so if we do this sort of mirroring operation to each of them, we get 3, -3, 4, -4, 5, -5. And these are going to be exactly the eigenvalues for these three matrices. And I mean, you can convince yourself pretty easily that these are Hermitian. And I mean, because all of the elements that are not on the antidiagonal are 0, they're all in our version of SP2N. And A plus B is indeed equal to C. And the eigenvalues line up. So that's the same. So these also solve a matrix eigenvalue problem, which is also pretty nifty. So before we talk about the main result, which is a extension of the Horn inequalities, I just want to quickly plug some work that was done before us that is also worth mentioning. So in particular, in 1997, Littleman came up with the Littleman path model, which is a way to compute tensor product multiplicities for any compact semisimple Lie group. So that is an extension of our result in a couple of different ways. So firstly, the classical groups are a subset of these groups. So in particular, it computes tensor product multiplicities for that. And specifically, the Littleman path model also does this outside of the stable range. So for this talk, where the Newell-Littlewood numbers live entirely in the stable range, because we know some weird stuff can happen beforehand, and the Littleman path model calculates even that. So in a sense, that completely solves this the problem of these Newell-Littlewood numbers in the same way that the Littlewood-Richardson rule completely solves the Littlewood-Richardson problem. However, just like before, sometimes we're not necessarily concerned with the exact numbers themselves, but when are these numbers 0 versus non-zero? Because we find that sometimes computing that is a significantly easier proposition and all we care about. But even that problem has been solved by work of Balkali and Kumar back in 2006, they came up with the Balkali-Kumar inequalities, which describe the saturated tensor cone for any semi-simple Lie group. So that, which again solves even that reduced problem. Their solution is good. It solves the problem. But something to note is that their inequalities rely on these Balkali-Kumar coefficients that are, for which the Newell-Littlewood numbers are a specific case, but contain other coefficients. And their inequalities that define the Newell-Littlewood semigroup, the saturated one, involve these other coefficients. So in order to compute the Newell-Littlewood numbers and like whether or not you have a Newell-Littlewood triple or not, you need to know coefficients. You need to know things that aren't the Newell-Littlewood number. You have to go outside the scope of the problem. So our version of the Horn inequality is entirely self-contained. Our work is based on this, but it does not follow immediately from it. So without further ado, these are the extended Horn inequalities. Now, these look much more complicated, but hopefully I'll be able to make sense of them for you guys. So unlike the usual Horn inequalities, which were just parts of nu is less than or equal to parts of lambda and parts of mu, we know that the Newell-Littlewood numbers are symmetric in all three partitions. So we would expect this formula to work under exchange of the different partitions. So in particular, you would need lambdas, mu's, and nu's on both sides of the inequality. And here, once again, we have three conditions. The first condition is just saying you don't want lambda to be on both sides, the same part of lambda to be on both sides of the inequality. You don't want to add the same thing to both sides of the inequality. The second condition is just a size constraint. It's just a fancier version of the condition before that the three sets had to be the same size. Now we have a slightly more complicated form for it. And then the third condition is the weirdest, is what I'd say. So this is the equivalent of saying that the taus of the three sets form a Littlewood-Richardson triple. Here, we need the tau, we have 6 sets, and we need the sort of 6-way product of the taus of these sets to be non-zero if you sum over all possible ways to fill out the bottom. So this isn't the obvious choice for a recursion. I mean, what we'd like is something like the Newell-Littlewood numbers of the taus are non-zero. But again, because the Littlewood-Richardson coefficients are just a special case of the Newell-Littlewood numbers, this is actually fully recursive. So we conjectured, me and my co-authors conjectured this form for the extended Horn inequalities last year. And then this year, we were able to prove that these exactly describe the saturated Newell-Littlewood semigroup. So just as a quick example, I have over here the extended Horn inequalities for n equals 2. There are 18 of them, which is a lot, but a lot of them are actually simple. So you can see that these are the 3 Horn inequalities we were talking about before, and these are each contained in the extended Horn inequalities, which makes sense because, again, LR coefficients are special cases of NL numbers. So you would expect things that are necessary and sufficient for those to show up here. And not just the original Horn inequalities, but again, we're symmetric in all 3 variables. So we need the symmetric shifts of all 3 of the variables to be, of all 3 partitions to be extended Horn inequalities. And then we also have this trace equation, again, for the Horn inequalities, turning into this version of the triangle inequalities. So it doesn't, so it's not a 1-for-1, but what was an equation is now an inequality. And then lastly, we have these 6 other extended Horn inequalities, which don't correspond to the usual Horn inequalities. These specific ones we've called the extended Weyl inequalities. But the short of it is, as n gets larger and larger, the extended Horn inequalities that don't correspond to Horn inequalities make up a more and more significant portion of the extended Horn inequalities. So by understanding the Horn inequalities and like the Littlewood-Richardson semigroup, that doesn't give you a large amount of information to understand the Newell-Littlewood numbers, which is what we would expect. So the last thing I want to talk about is that is redundancies. So if you want to just do a problem on your own time, you can convince yourself by going through the rules that this inequality over here is an extended Horn inequality. It checks off all the boxes, but lambda, mu, and nu are partitions. So lambda 2 is always going to be less than lambda 1. Mu 2 is always less than or equal to mu 1. Nu 2 is always less than or equal to nu 1. So even ignoring the lambda 3, mu 3, and nu 3, this is already a redundancy with some extra stuff tacked on. And even worse than that, it's not even just redundant in terms of other extended Horn inequalities. This is actually just trivial from the definition of partitions. Knowing literally nothing else about the Newell-Littlewood semigroup, you would say, oh yeah, that's obviously going to be redundant. So luckily we do also have we do have a form for that. It's a little bit more complicated. So we still have that all the things are the same form, all the inequalities are the same form for our irredundant version of them. We still have this disjointness condition. The size condition is a little bit different. It's a little bit stricter. So now we force the sizes to have a bit more of a property. And then we have this last condition where before we had, so if you remember for the regular Horn inequalities, we just had that the Littlewood-Richardson coefficients had to be exactly 1 to be irredundant. Here we have that 2 Littlewood-Richardson coefficients have to be irredundant. But again, we have 6 sets. So how do we square that with a Littlewood-Richardson coefficient only taking in 3 inputs? Well, there are these 2 sort of extensions of our tau function from before, tau 0 and tau 2, and the definition for them is a little more complicated, so I won't go into them right now. But what they do is, instead of taking in 1 set and spitting out a partition, they take in 2 disjoint sets and spit out a partition. So what we can do is we can compute so if we know that I and I prime are disjoint. So if we do tau 0 of I comma I prime, that's a partition. So then by doing this tau 0 for the 3 pairs of disjoint sets, we have to get a Littlewood-Richardson triple that outputs a 1. And for the other one, we have to do the same thing for tau 2. So we not only have these extended Horn inequalities, we have an irredundant set of them. So yeah, that's what I have. Thank you.